Welcome back to my channel. In this video, we will be discussing seismic waves. Seismic waves are waves of energy that travel through the Earth's layers and are the result of earthquakes, magma movement, volcanic eruptions, large landslides, as well as large man made explosions. The study of the passage of seismic waves through the earth is known as seismology. In this video, we will be focusing on seismic waves associated with earthquakes. An earthquake occurs when pressure builds up along fault lines and is then suddenly released. The point at which the energy is released is called the focus or hypocenter. The energy which is released at the focus travels through the earth as seismic waves and reaches the surface first at the point directly above the focus called the epicenter. Seismic waves can broadly be divided into body waves and surface waves. Body waves, which include P waves and S waves, are transmitted upwards to the surface from the focus of the earthquake. When body waves reach the surface, some of them are transformed into surface waves. Surface waves can also be generated when the source of the earthquake is close to the Earth's surface. The two most common types of surface waves are love waves and Rayleigh waves. Let's talk a little more about body waves. A body wave is a seismic wave that moves through the interior of the earth. They travel along paths controlled by the material properties of the earth's interior. When we describe these waves, we can talk about how the particles move in relation to the direction of wave propagation. In the diagram, the white arrows show the direction in which the waves propagate. Notice that the P wave shown at the top, notice for the P waves shown at the top, the particles respond to the wave by moving parallel, that is, in the same direction to the wave propagation. On the other hand, the S waves being shown at the bottom, the particles move at right angles to the direction of propagation of the wave. Let me say that again. For the S wave, the particles move at right angles to the direction of propagation of the wave. Now, the P in P waves could mean primary, it could mean pressure, or it could mean push-pull. Push-pull describes the way particles respond as the P waves move through the earth. Notice that the P wave alternately push or compress and pull or extend the ground as they move through. The P in P waves also stand for primary. This is because P waves travel faster than other waves through the Earth and therefore arrive at seismograph station first. These waves can travel through solid as well as liquid and gas. They travel nearly 1.7 times faster than S waves. In air, they travel in the form of sound waves. Hence, they travel at the speed of sound. The S in S waves stand for secondary, share, or shake. Notice that as the S wave passes through the Earth, the particles shift in a right angle direction to the direction of propagation. S waves are also called secondary waves since after an earthquake event, they arrive at seismograph stations only after the faster P waves, hence secondary. The speeds of S waves are typically around 60% of the P waves. The S also indicate that the wave involves shear stress. Since fluids such as liquid and gas do not support shear stresses, S waves can only travel through solid materials. Now, this graph shows the velocity of body waves in the Earth versus the depth of the Earth. Notice that while the P waves are present at all layers of the Earth, the S waves are absent in the outer core, and this is because the outer core is liquid. The term surface waves refer to seismic waves which do not penetrate in the deeper interior of the earth, but rather travel just below the surface of the ground. These waves spread from earthquake epicenters and are normally generated by shallow earthquakes. Surface waves are larger in amplitude and longer in duration than body waves, but they move more slowly. As such, they arrive at seismograph stations after the arrival of P and S waves. Now, one type of surface wave is love wave. Love waves are named after A.E.H. Love, the person who discovered them. The small arrows in the diagram at the top are showing particle motion. The particle motion in the love wave is parallel to the surface but perpendicular or right at a right angle to the direction of propagation indicated by the larger blue arrows. Love waves have the same motion, therefore, as F waves, but without the vertical displacement. They move the ground from side to side in a horizontal plane, but at right angles to the angle of the direction of propagation of the wave. Love waves are very destructive and can be particularly damaging to structures due to the horizontal ground motion they generate. Love waves travel at a speed that is usually about 10% slower than S waves. But like S waves, they cannot spread through water. However, they usually travel slightly faster than Rayleigh waves. So love waves arrive before Rayleigh waves at seismograph stations. Love waves cannot exist in a uniform solid. Hence, their existence is proof of the Earth's vertical inhomogeneity. They can only occur when there is a general increase of S wave velocity with depth. Now, onto the second type of surface waves, which we have mentioned before, the Rayleigh waves. Rayleigh waves were discovered by British physicist John William Stott, who predicted their existence. After his father's death, Stott inherited the title Lord Rayleigh. The wave was therefore named after this title. Rayleigh waves are descriptively called ground roll in exploration seismology. They spread through the ground as ripples similar to rolling waves on the ocean. The velocity of Rayleigh waves is not constant but varies with wavelength. However, they are slower than body waves and are generally slower than love waves as well. This means that they are usually the last to arrive at seismic stations. Seismic waves are measured at seismic stations. They are detected and recorded by seismographs, which measure, amplify, and record the motion of the ground. The information is used to determine earthquake locations, the subsurface structure, and so on. A seismograph is an instrument that constantly records ground movement. Separate seismographs are needed to record side to side movements and up and down movements. A pendulum mounted seismograph, as shown at the bottom, is a seismograph that measures side to side movement. It has a heavy weight hanging from a wire. The weight remains almost still as the ground moves back and forth beneath it. A pen attached to the weight records the movement. A spring-mounted seismograph, shown at the top, is a seismograph that records up and down movement. It has a heavy weight hanging from a spring. As the ground moves, the weight stays almost still as the spring absorbs the movement by getting longer or shorter. A pen attached to the weight records the changes in distance between the ground and the weight. Now, the recording produced by a seismograph is called a seismogram. The recording looks like a series of wiggles in a line. The seismogram shows the arrival times of the different waves. As we would expect, we first see the arrival of the P waves, which travel the fastest. This is followed by the S waves. Surface waves, which travel at the slowest speeds, are the last to arrive. The height of the wiggles in the line indicate the amount of ground movement produced by seismic waves at the seismograph's location. This is called the amplitude of the waves. The patterns in the wave data is critical in determining the nature and location of earthquake. By studying seismograms, scientists can determine the locations and strength of earthquakes. Scientists use triangulation to find the epicenter of an earthquake. Timing when each wave arrives at a seismic station can help locate an earthquake. First, the arrival times of the P and S waves are found from 3 seismic stations. The difference in the arrival times between the P and S waves for each station is calculated and then matched with their corresponding distances on a distance time graph as is being shown. Now, this distance found on the distance time graph could be in any direction from the station. So, another step is needed to determine the direction. To do this, circles are drawn around the seismograph locations using the distance between the P and S waves as the radius. The point where these 3 circles intersect indicates where the earthquake originated. In order to compare different earthquakes, we can talk about magnitude as well as the intensity of the earthquake. The magnitude measures the energy released at the source of the earthquake and is determined from the measurements on seismographs. Intensity, on the other hand, measures the strength of shaking produced by the earthquake at a certain location and is determined from effects on people, human structures, as well as the natural environment. Magnitude remains unchanged with distance from the earthquake. However, intensity decreases with distance from the earthquake epicenter. Magnitude measurement requires instrumental monitoring for its calculation. It is most often measured using either the Richter scale or moment magnitude scale, which we will discuss soon. Earthquake intensity is measured on the modified Mercalli intensity scale, which is based on the extent of damage caused by the earthquake to both natural as well as man-made structures in the landscape. Now let's talk a little about the Richter scale as well as the moment magnitude scale. From 1935 until 1970, the Richter scale was the main scale used to measure earthquake magnitude. The Richter scale uses a mathematical formula invented by seismologist Charles Richter to compare earthquake sizes. The formula is based on the amplitude of the largest wave recorded on a specific type of seismometer and the distance between the earthquake and the seismometer. However, the Richter scale has a number of limitations. For example, it goes up to a maximum magnitude of 7 meaning that all larger earthquakes would always have a magnitude of 7 or less. Also, the Richter scale only describes the maximum wave amplitude and does not give any indication of the total energy that is released by the event. The Richter scale worked largely for earthquakes in Southern California, where it was developed, and only those occurring within about 370 miles of seismometers. In addition, the scale was calculated for only one type of earthquake wave. Though the Richter scale is still used for forecasting future earthquakes and calculating earthquake hazards, it has largely been replaced with the moment magnitude scale, which records all the different seismic waves from an earthquake on seismographs across the world. The moment magnitude scale measures the movement of rock along the fault. It accurately measures larger earthquakes, which can last for minutes, affect much larger areas, and cause more damage. Now, as you must have realized from the lesson so far, seismic waves do not just result in earthquake disasters, but are also very useful to us. Let's look at some of the ways in which seismic waves are valuable. Through the use of triangulation, seismic waves can help us to locate the source of an earthquake. They help us to better understand the structure of the earth based on the way they respond to the variations in the earth's geology. Seismic waves are also useful in mineral exploration by giving us a picture of what is under the surface. It therefore determines not only where to mine, but also how to mine. The movement during an earthquake can help oil and gas reservoirs to get punctured and seep through this new structure. This may bring them to shallower depth where they can be exploited more easily. Seismic waves also tell us what is happening in magma chambers and therefore allow scientists to monitor volcanoes and the threat of eruption. Seismic waves also help to create faults, which in turn contribute to the creation of landscape features such as mountains and valleys. Okay, I hope that you learned something. And as usual, I would encourage you to attempt a few past paper questions using the information from this video. So thanks again, and remember to like, share, and subscribe.